Hey guys, in today's video we're going to be integrating sin x over x from 0 to infinity, so we'll be evaluating this integral. Now if you notice, we've actually covered this integral on the video on the channel before. However, today we're going to be using a different technique. So in the previous video we used complex analysis, so basically we integrated over a semicircle in the complex plane. In today's video, we're going to be using the Leibniz rule, or differentiation under the integral sign, otherwise known as Feynman's technique of integration. Now, basically how you start this is pretty much you parameterize it. So parameterize means is we basically add in another variable and basically make this integral a function of something. So in other words, we're going to make it a function of alpha. So f of alpha is something. So now we've got to pick where we want to put this alpha. Now, the best place to put the alpha would be here. The reason why it would be there is because when you differentiate it, well, when you want to find f dash of alpha, you need to use a partial derivative. And then if you differentiate this with respect to alpha, you'll get an x, which will cancel the x on the bottom, and you'll have a nice integral. However, from that point onwards, it gets pretty hard to integrate because what you're left with is pretty much an improper integral like this, from 0 to infinity of, let's say, sin x over alpha x. Now that's kind of hard to integrate because, one, if you put in 0 into here, that's going to give you 0, and if you put in infinity into here, well, sine of infinity, that basically oscillates between 1 and 0, depending on what value it is, so it doesn't really help us either. So putting the alpha here isn't the best move. Now, what's a better move is we can do some algebra manipulation. So we all know that if you differentiate e, or e to the x, you're going to get e to the x. However, if you differentiate this and you have like a number up here, the number comes down the front. So if we have, let's say, e to the alpha x, and you want to find the partial derivative with respect to alpha, then the x will come down the front. Now, this might pose another problem. So when we plug in our values into here, if we put in infinity into here at some point, that's just going to blow up to infinity, which doesn't work very well. What makes it even better is if we put a negative sign here, then if we put an infinity into here, this entire term goes to 0, because if you have infinity over e to the negative infinity, this is going to approach 0 faster than it approaches infinity, because this term will approach infinity faster because it's an exponential term and this is only a linear term. So what we do to set up this integral to make this really nice and easy is pretty much we're going to pretty much put in an Euler function. So in other words, we're going to go f of alpha is equal to the integral from 0 to infinity of sin x over x multiplied by e to the negative alpha x dx. Now, what does this mean? So this means our original function here is f of 0, because if you put the 0 into here, then this whole term goes to 1, which gives us our normal integral. So yeah, we haven't really changed anything, we've just made some adjustments that makes it easier to pretty much apply the rule. So what we do now is pretty much we differentiate. So we find f dash of alpha. So when we do this, we pretty much get a differential on the outside. And what we can do is pretty much we can bring it inside the integral, and that turns it into a partial derivative. So I'm just going to skip this step, so I'm actually just going to bring it straight on the inside just to save some writing room. So we have the integral from 0 to infinity, and then we have the partial derivative of alpha, and it's affecting all of this. So sin x over x, and then e to the negative alpha x, and then dx. Now, with the partial derivative, you basically treat the other variable as a constant. So x's are all constants now. So that's a constant. So the only function we have here is an Euler. So what we do pretty much is we differentiate this. So the way we differentiate this is this x, this negative x, will come down the front. So what we're left with is, alright, f dash of alpha is equal to the integral from 0 to infinity of sin x over x negative x e to the negative alpha x. Now, what can we see what's already happened here? That's cancelled and that's cancelled. So now we have a really easier integral to deal with. Now you might not think it looks easy because you think, alright, we've got two variables in there and it looks like we have to do some integration by parts. Now, yeah, we do have to do some integration by parts, but it's not as bad as you think. You just got to take it slow pretty much. So, this is what we have now. So we've got a really nice integral setup, and now we've got to do it by parts. So integration by parts, you've basically got to pick one thing to choose to integrate and one thing to choose to differentiate. Now, the best thing to do here is to choose the Euler one to differentiate, because if we integrate that, we're going to have a 1 over alpha here, which is going to make it really yucky. So what I'm going to do is pretty much, alright, I'm going to let u equal e to the negative alpha x. Therefore, I'm going to let, well, dv x equal negative sine x. Now the reason why I didn't pull the negative out the front is because if I integrate this, it's going to give me exactly cos x. Now if I differentiate this, I'm going to get du dx is equal to negative alpha e to the negative alpha x. Okay. Now the formula for integration by parts is pretty much these two bits here multiplied together, so we'll have square brackets, so e to the negative alpha x cos x, and then we have a bracket 0 to infinity minus these two bits here. So then we have minus, now we've got a negative here, so we can turn that into a plus, pull the alpha out, and we have the integral from 0 to infinity of e to the negative alpha x cos x. Righto. So hopefully that all makes sense. I'm going to rub this out just to have some room. Now let's evaluate these square brackets here. What can we actually do with these? So if we put in infinity into where x is, it's actually going to be really nice, because what we're going to have is cos x over e to the negative alpha x. Now if you let x approach infinity in here, while this term's just going to oscillate between negative 1 and 1. However, this term here is going to get really large, so therefore this entire term will go to 0 as x gets really large. So that goes to 0, and then we have minus, and then we put in 0 here, so we'll have cos of 0 over e to negative alpha times by 0. This will just turn into 1, and cos of 0 is just 1, so we have 1 over 1, but you have the negative sign in front of it, so this entire square brackets here is just equal to negative 1. Right, so I'm going to rub that out now, we don't need that. Now, you might see, we've got pretty much an oscillating thing happening here with our integrals. As you can see, this function here doesn't disintegrate when you disintegrate when you differentiate or integrate. Neither does this one, they cycle between each other. But what the beauty of that is if we integrate this here, we're going to get a very similar thing over here, which is going to allow us to use some algebra manipulation. So what we're going to do here is pretty much we're going to take this integral and do parts on it. So if I write this integral from 0 to infinity of e to the negative alpha x cos of x dx, I'm going to choose the exact same things as I did before. So I'm going to let my Euler one equal my u. So u is equal to e to the negative alpha x, and I'm going to let dv dx equal to cos of x. So if I want to differentiate this, it's going to be du dx is going to be equal to negative alpha e to the negative alpha x. If I integrate this, it's going to give me exactly sine, so v is going to be sine x. So therefore, if I'm writing this one out, I'm going to move this to the side real quick. This is going to be equal to square brackets e to the negative alpha x sine x from 0 to infinity minus, now we've got a minus here, so we can turn that to a plus alpha, the integral from 0 to infinity of e to the negative alpha x sine x. Oh, I'm running out of room. I've got to move this. Sine x dx. Now, we can see that this is actually exactly the same as this. So, we've got some pretty much patterns appearing here. Now, we've got to work out what this is going to be. So, if you put in sine of infinity in here, that's going to oscillate. But if you put in if you put in infinity down here, you're going to get 0. So this whole term will go to 0 because this number will get very large, and 1 or negative 1 over a really large number approaches 0 pretty much. Now if you put in 0 into here, you're just going to get, well, sine of 0 is 0, and then you'll have 0 divided by 1, so that's just 0. So this entire square brackets here disappears. So what I can do here is pretty much rub all that out, because it's not going to be, there's nothing there pretty much. So what we have here is pretty much, alright, our little pink box over here is just equal to pretty much a multiple of what we have over here. So in other words, if I rewrite this all out, so move that, and let's move this to the side. So if I take out a negative sign here, I'm going to have negative the integral from 0 to infinity of sine x of x e to the sine x of x e to the negative alpha x dx. So I'm just writing this bit here is equal to negative 1 plus alpha multiplied by all this, and all this is just this here, so we actually have alpha squared, the integral, and all this here. So what I can do is rub that out and just move this next to it. So now you're probably thinking, this looks really hard to solve, we've made it even worse. Not really. We can just think of these integrals as just numbers. We know this will evaluate to something, and we know this will also evaluate to something. So what we're going to do is pretty much rearrange it so we get the integral as your subject. So the way we do that pretty much is, alright, move this whole thing to the other side. So we're going to have negative the integral from 0 to infinity of sine x e to the negative alpha x dx minus alpha squared, the integral from 0 to infinity sine x, I'll write them exactly the same so you can see how exactly the same they are, dx is equal to negative 1. Now you can see there's negative 1 here, negative 1 here, negative 1 here, so that can cancel, that can cancel, that can cancel, so they all turn to pluses. And you can see we have alright, we've got sine x e to the negative alpha x here, and we also got the same thing here, so we actually take out a factor of this integral. So if we take out a factor of this integral, what we're left with is pretty much that multiplied by 1 plus alpha squared is equal to positive 1. And then all we got to do is divide by 1 plus alpha squared. So the integral from 0 to infinity of sine x e to the negative alpha x dx is equal to 1 over 1 plus alpha squared. Now you're probably thinking, alright, this isn't f dash of alpha, because f dash of alpha was just negative the integral from 0 to infinity of all this. So all we've got to do to turn that into f dash is just put a negative here and put a fat negative there. So we've got to move this and just put a negative there. Then we can equate them. So we can say, alright, this is f dash of alpha is just negative all this. And as you can see, this is going to be an arctan here. So recall, if you integrate something like this, so if you have 1 over 1 plus a squared, or if you have a plus, sorry, what is it? If you have a plus 1 over a squared dx, that's just going to be tan inverse of a, okay? What we have here is actually something very similar. So as you can see here, what was it? Oh, sorry, forgot. That's going to be an x. There we go. That makes much more sense. So in this case here, a and a squared is 1 because a squared is equal to a because a is 1. So if we integrate this side, so we're going to have f of alpha then. Integrate this side, take the negative out the front. So we have 1 over 1 plus alpha squared d alpha. What we're going to get is f of alpha is equal to negative arctan of alpha plus c. Now we know what f of alpha is. We wrote it up here. It's this. So this is equal to the integral from 0 to infinity of sine of x over x e to the negative, I just got to remember what I wrote, alpha x dx. It's equal to negative arctan of alpha plus c. Now, we're almost done. We just got to work out what this c is. Now, you're probably thinking, alright, what numbers can we plug in to work out what c is? Well, if you recall, if you put in a really large number into here, you're going to get pi over 2. Because tan inverse of a really large number will approach pi over 2. So if it was a and the limit was as a approaches infinity, this tan inverse of a would be equal to pi over 2. Now, if you put in infinity in here, not only does this give a numerical value, but this also makes this entire thing equal to 0, because if you put infinity up here, you're going to have it down here, so you're going to have sine x over x divided by a really large number, so you're going to have 0 over this side of the integral, and if it gives you a numerical value over here, then you can rearrange and work out what c is. So what we're going to do is pretty much let alpha equal infinity. Now that might be uncomfortable, but you could just say, all right, alpha is equal to a, and a approaches infinity. But just for easy sake, I'm just going to say alpha is infinity. So alpha is equal to infinity. So if we put infinity in here, sine of x over x multiplied by e to the alpha, infinity multiplied by x dx, that's going to go to 0. And if you put infinity into here, so tan inverse of infinity will be pi over 2, 90 degrees otherwise. So what we have here is 0 on this side. So 0 is equal to negative pi on 2 plus c. So therefore c must be pi on 2. So therefore the integral from 0 to infinity of sine x over x e to the negative alpha x dx is equal to negative arctan of alpha plus pi over 2. Now our original integral was sine x over x, so this was just f of alpha. We wanted f of 0. So if you put in 0, we're going to have the integral from 0 to infinity of sine x over x dx is equal to negative arctan of alpha, and alpha is 0, so arctan of 0 is just 0, so this is equal to pi on 2. And that's our answer. And if you wanted to know to negative infinity, just double this, so it's just going to be pi. Righto, so that was sine x over x completed using Feynman's technique of integration. I actually prefer this technique over the other one.